Good afternoon, everyone. Today's class, I'll be taking the topic of capacitor. So, let's see what a capacitor is. A capacitor is a simple device which can be used to store charges. There are two plates in a capacitor. So, I will draw it here. There are two plates which are parallel to each other, somewhat like this. Such a capacitor having two parallel plates is called a parallel plate capacitor. So the plates here are of equal length and equal area. One of the plate has positive charge spread throughout it. The other one has negative charge spread throughout the plate. So the charge density of these plates can be written as, for the one at the left, the charge density sigma is Q by A. Q here is the charge which are spread over the plate. A is the area of this plate, this cross-sectional area. Here you have negative charges spread over another plate. The charge density of this plate is also Q by A. The charge density of both the plates here are equal. But negative are, one of that is negative, the other one is positive. So the charge densities are opposite in nature. So when you have a parallel plate capacitor, then we can store charges here. You can see at one end you have positive and at another end you have negative charges. So this acts as a way of storing charges. So how much charge a capacitor can store? Q is the charge the capacitor can store. Per unit potential difference, delta V, or I can just write it as V for now, So it will give you the capacitance of the capacitor, So if a particular capacitor can store a large amount of charge, or in a very small potential difference, in between the plates, then it has a very high capacitance. And why is there a potential difference in between the plates? Because one plate is positive, which is at higher potential, while the other one is negative, which is at lower potential. So there's a difference in electric potential. So electric potential difference exists in between the plates. So if you can accumulate more charge on this particular potential difference, you get a very high capacitance. So C is given as Q by V, where C is the capacitance of this capacitor. Q is the charge of this capacitor. So the charge here Q is the charge of any one plate. You can take it as the charge of the positive plate or the negative plate. We are talking about the magnitude of charge. So it's not the addition of the charges, because when you add the charges you get 0, because you have equal positive and negative charges. So let's find out C for parallel plate capacitor like this. So to get C, we must first find out potential difference that is present in between the plates. To find out the potential difference that exists in between the plates, we must know what the electric field is in between the plates. So in electrostatics, we have studied that the electric field of a plate, is sigma by 2 epsilon. So the plate here, the one with negative charges, will have this electric field around it. So at any region, let's say here, region A and region B, and let's say region C. C lies in between the plates, A and B lies outside of the plate. In region A, the electric field due to the plate with negative charge is, so electric field A will be sigma by 2 epsilon due to this charge. And we know the electric field due to a plate doesn't vary with the distance from the plate. There is no variable here, like which takes that into account. It's constant for whatever distance, whether it's nearer or farther away from the plate. So at point A you have this much electric field due to the negatively charged plate. Like at point A you also have electric field due to the positive charged plate here. Right. So if the electric field is sigma by 2 epsilon naught, it's directed towards the left. Right. To show it I can use minus here. Right. And the electric field due to the positively charged plate at A is directed to the right. Right. So for showing something towards the right, I can use the positive sign here. So it's plus sigma by 2 epsilon naught. Right. The electric field due to both the plates are equal in magnitude, but are opposite in direction. So the net electric field at A is 0. Okay. So there's no electric field outside of the plates at A. Even at B you have the same thing. Okay. E at B is also sigma by 2 epsilon naught due to the positive charge plate, minus sigma by 2 epsilon naught due to the negative charge plate. So you get 0. Right. So let's see whether there is any electric field within the plate or not. So E at C. Right. At C, the electric field is directed to the right. Okay. Due to the positive plate, and it's also directed to the right due to the negative plate. So at C, the electric field due to these plates, they add up instead of getting cancelled out. So there exists an electric field at C. So E at C is what? E due to the positive plate, which is sigma by 2 epsilon naught, plus E due to the negative plate, which is sigma by 2 epsilon naught. Since both the electric fields are in the same direction, right? So we take positive for both. So when you add them up, you get sigma by epsilon naught as the electric field within the capacitor, right? So this amount of electric field, sigma by epsilon naught, exists here in between the plates, right? What about the potential difference due to the electric field? Okay, I can use delta V, or I'm just using V here. Okay, V here stands for potential difference in between the plates. So we know from electrostatics that the potential difference within the plate is E times electric field multiplied by the distance of the plates from each other. Right. So from here, let's say D is the distance in between the plates. Right. So E is sigma by epsilon naught into D is, let's keep it as D. Right. So we get V, the potential difference in between these plates, as sigma by epsilon naught times D. Okay. So we can now find out the capacitance. So C will now be Q by V. Q can be written as sigma times area, because we know charge density sigma is Q by A. So charge is sigma into area. Right. So V is sigma by epsilon naught into T. So from here we get C as A epsilon naught by T. So the capacitance of a capacitor can be found out from this expression here. Right. If you know the area of the plates A, if you know the area, the distance by which the plates are separated, then you can get the capacitance of the particular capacitor. Right. Epsilon naught is the permittivity of free space. Right. So it's a constant whose value we know. Okay. So this way you can get the capacitance of a capacitor. So we can see from here that the larger the area of the plate, the more the capacitance the capacitor will be having. Okay. And the further away the plates are separated, the lesser the capacitance the capacitor will be having. Right. Okay. So let's see what series and parallel connection are. When you have two capacitors next to each other, next to each other. Okay, there can be more than two. Okay, I am taking two for now. One of the plate is positive, the other one is negative. Positive, then negative. So if capacitors are arranged in this way, placed next to each other, then you have capacitors in series. Okay. If capacitors are placed parallel to each other, like this way, plus here, minus here, plus here, minus here, right? Then you have a parallel connection, right? So let's look at the parallel connection for now. The capacitance of a parallel connection, let's say CP, okay, is it the sum addition or the sum of the individual capacitance? So for let's find out, right? Both the capacitors here are at the same potential difference V, right? So we know C is what? Q by V, no? Right. So the potential difference of both the capacitors are the same, but you have two capacitors here. So the charges that you have here is twice that of one capacitor. Right. You have double the charge. So C becomes what? 2Q by V. Okay. So that means the capacitance of capacitors when connected in parallel, okay, they get added up. Right. So when you have two capacitors in parallel, right, their capacitance gets added up. Okay. So I can write that the capacitance of capacitors in parallel Cp is C1 plus C2, where C1 is the capacitance of the first capacitor and C2 is the capacitance of the second capacitor. Right. But what about series connection? When capacitors are in series, okay, then the potential difference you have here across the first capacitor and then across the second capacitors are not equal. Right? Since they are connected in series, okay, one of the capacitor may take up a larger potential than the another one. So the potential difference are unequal, right? But the sum of the potential difference will be equal to the EMF of the cell, right? So if these two capacitors are connected to a cell having EMF V, like with no internal resistance, right, then we can equate the potential difference of these capacitors to V, okay? Because the potential difference of the cell, it got divided into these two potential differences, okay, which are used by these resistors. So V is equal to V1 plus V2. So V is the Q by C. You can write V as Q by C. Okay, Q is the charge on each of these capacitors, and in series connection, the charges that get accumulated in the capacitors are equal for all the capacitors. Right. So you have Q by C in series is equal to V1 is Q by C1 plus V2 is Q by C2. From here we get 1 CSS 1 by C1 plus C2. Okay. This is for series connection.